Hello, my name is Brandon Annan. This presentation is part of an online course from Coursera and Duke University on machine learning foundations for product managers. We'll be predicting the electrical energy output of a combined cycle power plant. Our agenda follows the CRISP process with business understanding, data preparation, modeling, evaluation, and deployment. Our desired outcome is to predict the electrical energy output of a combined cycle power plant that can be used for various purposes, which may include lower emissions, lower cost per megawatt hour produced, financial planning, or managing peaker plant usage. Regression error metrics including mean squared error, mean absolute percent error, and R-squared will be used. The dataset features include temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. The dataset observations include 9,568 hourly average ambient environmental readings obtained from sensors. To get further understanding of the data, a correlation heat map has been created. Temperature and exhaust vacuum have a high negative correlation on decreased energy output. Ambient pressure and relative humidity have a positive correlation on increasing energy output, though the relative humidity has a weaker influence. One thing to note is a strong correlation with temperature and exhaust vacuum decreasing energy output, which is worth further investigation. Using a simple linear regression model reviewing temperature and exhaust vacuum on energy output confirmed a strong linear influence on PE, though at slightly different rates. Model selection will be key as temperature and exhaust vacuum's strong influence on energy output might confuse some models. There will be no special data preparation done as all features are determined relevant, data resides within the ranges provided in the assignment, and no need for reformatting. A simple Python script confirmed the data was within ranges. For the modeling task, a simple linear regression model uses split data for training, validation, and testing. Regression metrics are captured on both the validation and test data. While basic linear regression model may have hyperparameters, the script did not explicitly set or change them. The ridge linear regression model was applied to the data set to observe the strong influence on temperature and exhaust vacuum on energy output. Data is again split into training, validation, and testing, along with regression error metrics captured on validation and test data. Using the sklearn grid search CB API, the alpha parameter, referred to as lambda in the course, helped determine a value of 10 for this model. No other hyperparameters were set or changed. Turning to our random forest regression model, this ensemble method employs multiple decision trees to counter overfitting, boost accuracy, and observe the temperature and exhaust vacuum influence on the energy output. By averaging the predictions across various trees, the model neutralizes individual biases from these features, enhancing stability and reliability in predicting energy output. Complexity is controlled by setting the hyperparameter in estimators to 100 trees. Bagging was not used to a technical issue, though I do believe that would have had a positive influence on the final results. As mentioned in the business understanding, regression error metric outputs MSE, MAE, MAPE, and R-squared have been collected on the test data for the evaluation phase. The test data, which is not included in the training of the model, provides insights when comparing models as it ensures performance assessment is unbiased and reflects how the models would perform in a real-world scenario. The results were enlightening. As the data on the slide indicates, linear regression and ridge regression have very similar results and could not observe any special influences temperature or exhaust vacuum observations may have had on the energy output. The random forest model significantly outperformed the linear models as seen in the regression error metrics. The superior performance of the random forest model is attributed to its ability to handle complex data interactions more effectively than the linear models, capturing more nuances in the data, potentially seen from the impact of the exhaust vacuum and temperature observations on the energy output. Given these results, when we compare the accuracy and the predictive capability across models, random forest not only gives us a lower error rate, but also a higher coefficient of determination, R-squared, indicating a better fit to the variance in the data. The deployment phase report shows building a random forest model accurately and consistently predicts electrical energy output with reduced error margins. The model closely aligns to predict the actual power outputs, even across a wide range of values from 435 to 492 megawatts. This demonstrates the model's precision. Additionally, the model consistently delivers with a narrower error margins, as most predictions deviate by less than 15 megawatts from the actual figures. This level of accuracy ensures reliability in our predictions that are crucial for operational efficiency. Here are some additional outcomes related to strategic deployment advantages for energy output planning, scheduling, maintenance, and resource management. Thank you.